Good morning, everyone. Can you guys hear me at the back? Okay, perfect. So while the other people walk in, I'll just introduce myself. So I'm Naeemullah Khan. I did my master's and my PhD at KAUST. I left it in 2018, and currently I'm doing my postdoc at University of Oxford. So I work in computer vision and machine learning. And here in the WEP, I will give you guys a short introduction of what machine learning and artificial intelligence is, so that if you guys want to implement some machine learning or artificial intelligence algorithm for your work, you can actually start from this starting point, and you have at least some introduction of what kind of algorithms and methods to use. So the first thing that I need from you guys is to know what are your disciplines. So how many of you are from electrical engineering, computer science, and applied mathematics? If you can raise your hands. Okay, some of you. And how many of you are from biology, environmental science, chemistry, water desalination, and anything but SEMC? How many of you are not from SEMC? Okay. 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 So as I have guessed, majority of you are not from SEMC. So the level of the course is actually slight, very basic. So because we want to keep everyone with us. So I will start from the very basics and introduce and explain everything. But what I need from you guys is ask questions. So don't lag behind. If you don't understand something, raise your hand and ask a question. I don't mind. Okay, I'll answer the questions, and it can be a simple question, it can be a difficult question, I don't mind, but don't be shy. Okay, I want at least like 50 questions from today's session. Okay, just raise your hand and ask a question, and then it should be my job to explain anything that's confusing. Okay, so I think we are probably missing half of the class still, right? If I'm not wrong, but we will start, and as other people come, we will incorporate them. Go along. Okay. So the first thing, that we would see today is definitions, like what is machine learning, what is artificial intelligence, and what is deep learning. Okay. Then we will see a little bit of history of AI and machine learning. How has it evolved over, let's say, last 60, 70 years, particularly in the last 10 years. Next, we would see the motivation of the field. What happened in the last 10 years, 15 years? Why did it suddenly take off? Why has it started to working? It wasn't working before, and suddenly it has started working. Something must have happened, and we would see what these things are. And then for most of us, we would start our first actually step in machine learning. We would start with start with regression. So regression is a type of machine learning, and we will see what is regression and how we do regression and what is the goals of it. So the first thing, what is artificial intelligence, machine learning, and deep learning? Anybody wants to take a guess? You can say anything. Sometimes it's difficult for us to define as well, so no worries. Raise your hand and any guess. Okay, so I will introduce this like such. So in artificial intelligence, we write a computer program whereby a computer or a machine can sense, reason, act, and adapt. Okay, now that's pretty big bill. What does it mean actually? So it's basically, you can say that it's like a human baby, maybe around a year. So if you leave it in a room, it starts interacting with its environment. Of course, babies are much smarter than computer, but the basic principle for the machine and the baby is the same. It starts interacting with things. For example, if there is a candy on the floor, the baby picks it up, eats it, likes it. Now after that, he or she would start looking for candies. Okay. On the other hand, if there is, let's say, a power socket, the baby touches it, maybe gets negative reinforcement from the parent, the parents tell them not to touch it again. The baby probably would not touch it for the next 4 or 5 minutes. After that, he or she forgets what he or she has been told. I have a 1-year daughter, so I know the drill. It's really difficult actually to keep them away from something with negative reinforcement. You can, of course, give them positive reinforcement, and they actually do quite well. If you offer them something, some food or a poem or something like that, they definitely will come to you. So that's basically the broad definition of artificial intelligence. Let's say I have a robot in this room at this position, and the goal for the robot is, let's say, to go to the first chair in the 3rd row. Okay, and the robot knows nothing. It just knows that location, that when it reaches that location it will get a reward of, let's say, 1. Okay, other than that, the robot just knows the environment, how the room looks, but it doesn't know the steps to actually go to that position. So what the broad definition of artificial intelligence, we give the robot an algorithm to interact and move along in this room, and when it gets to that position it gets its reward. So the robot starts, maybe go a step further, hits a wall, realize that it cannot go further, either takes a left or right. Take the right, it takes the robot longer to go to the reward. Takes the left, it takes the robot less time to go to the reward, so maybe it would learn to go left. And then it repeats the process until it finds the right location. So basically the learning agent, the robot or the computer, would spend some time in this environment to actually find what is the right strategy to achieve a goal. Does it make sense? Basically you have an environment in which you put an agent and you give it some sensors, you give it some reasoning. Sensors is like, let's say, video data, maybe some sensors whereby it can detect obstacles and things like that. Reasoning is the computer, the program that we have written. Act is the motion, the steps that it can take. It can turn right, turn left, go forward, go back. And adapt is, for example, if it hits a wall, it knows that it cannot go any further. So it has to either take a decision to move left or right. So these are the 4 agents, like 4 steps of any artificial intelligence framework. Okay. Now, what we would be focusing more in this lecture is actually machine learning. And machine learning is a subset of artificial intelligence where we are focused on data. So basically what it means is that you have, for a process, we know what the input is and we know what the output for that corresponding input is. We just want the computer to learn that. So a simple example is, let's take the example of the robot that we just saw. So rather than leaving the robot here at this location, what we do is we provide the robot a lot of data. We tell it, okay, this was the path. If you follow that path, your reward would be 1. This is a path. If you follow that path, your reward would be, let's say, 0.5. So for example, if the robot goes directly to the right location, it gets a reward of 1 because it goes there in the shortest amount of time. Let's say if it takes a round trip around all of you guys, it maybe gets a lesser reward, 0.5. If it probably just oscillates here for some time and then goes there, maybe even lesser reward. But you have that data. You actually know which is the best path, the second best path, the best path, and so on. And you have a ton of that data. You give it to a computer, ask it to process it, and the computer learns something from it. Maybe a simple example would be, for a machine learning algorithm, let's say I want to find out, under the action of gravity in a time t, how much distance does an object cover? Okay, we know it from physics, it's half gt squared. Okay, but let's say I don't know it. I don't know what's the relation between distance covered and time under the influence of gravity. Okay, so what I do is I take a stone and I start dropping it from different heights. Of course, I'll get different times from it. I just collect the data of time and distance, and I give it a computer to figure out what to do with it. So basically I just collect some data, xi's, and the corresponding output, yi, and I just feed it in the computer. And then it's a computer's job to find out what the relation is. We don't actually care about it. Okay, there is some added caveat to it, but we will go to it next. But somehow, let's assume for the time being that if you have sufficient data, a computer can do the magic of learning what's the inherent relation between the data and its output. That's basically machine learning. Yeah. So for example, if some of you are working in biology and you have a process for which you have, let's say, 2 or 3 or 4 samples, you probably wouldn't be able to use machine learning very well because you don't have data. Machine learning is a science of data. You just need data, and hopefully if there is some relation in the data, the computer will learn it for you. And then there is a further subset of machine learning, which is called deep learning. So deep learning is machine learning with very big networks. So, well, you guys don't know networks yet, so I'll explain it in some other way. So in machine learning, you can allow the computer to learn something which is less general or more general. So something that is less general is easy to train. Something which is more general is difficult. So deep learning is the science of learning something which is very general. Okay? For the time being, let's just stick to this definition. As we go down, we would see exactly what it means. Less general and more general, what does it mean? Okay? 3 things. Artificial intelligence, computer can act, sense, and make the right decision. Machine learning, we don't want it to act, sense, we just give it data and we want it to learn what is important in that data. Deep learning, we do the same, but we want to learn something which is very general. Okay. Any confusion in it? Okay. Okay. So this is basically my understanding of the science that we have done so far. So we have 2 ways of studying a process or doing something with it. One is a model-based design, which we have used so far in our scientific advancement. So what is a model-based design? So it's basically a human observes a physical phenomena, observes some data, and then come up with a good model for it. For example, Newton observed an apple falling, and he realized that there is something to it. He did some experiment, and he came with equations of motion. Okay. In chemistry, I think I might be getting it wrong. I studied in high schools, but we get the spectrum of hydrogen. I think it was probably Bohr, and we realized that there are different levels of an atom in which an electron can revolve. Okay. We just saw something, and then we saw that there is a spectrum. A line in spectrum here, a line in spectrum here, and a line in spectrum here, and we realized that probably these are different levels of a hydrogen atom from which an electron can jump to another one and emit a light of a particular wavelength. So that's the model-based design. So model-based design is basically humans are the computer in that system. So we observe the physical world, the physical phenomena, we get some data from it, do something in our mind, and come out with a model for that process. And the second is the data-driven approach, or the learned way, in which we remove the human from the loop, put a computer there, ask it to observe a phenomena and give us a result. Now, of course, computers are not as smart as we are in observing the phenomena. So we have to actually make it slightly easy for it. And to make it slightly easy for it, we said that, okay, a human maybe observe 10 samples and make a judgment about it. A computer might observe 1,000,000 samples and make a judgment about it. But the advantage for computers is that computers can actually look at 1,000,000 samples. We cannot, because we do not have that fast a processor. They have a faster processor in order to crunch numbers and data. So that's basically the 2 approaches. So machine learning, artificial intelligence, and deep learning is the second data-driven approach, where a machine actually looks at the data in the physical world and tries to learn something from it. So basically, this is kind of the summary of machine learning. So basically, you have an input x, and you want to learn something y from it, a function which maps the input to the output. So the example that we saw, we had time and the distance covered under the influence of gravity. Okay, so let's say I'm just some approximate number. These might not be correct, but just to give you an idea. So let's say in 1 second, a rock falls 5 meters. Okay. 20 meters, 45 meters, and in 4 seconds it falls 16 times 5, 90 meters. Okay. Now we give this data to computer and we ask it to find the relationship between time and distance covered. So the computer has to find this f, which takes in an x, which is time, and returns a y, which is distance. Okay? That's basically machine learning in the easiest and simplest way. How do we do it is actually the question, but we will see how we do it. Okay. Any confusion here? So we know the input of the function, we know the output of the function, and we want the computer to learn that function. Okay? Has anybody seen something similar in their work up till now? Okay. Again, I would like comments, questions, so don't be shy. Okay. So model-based approach is what humans do. We observe physical process and produce mathematical models for it. Okay. And it's limited by our capacity to process data. So we cannot handle infinite data. We cannot not handle very large amount of information. And in machine learning, feature selection is less important. What it means is that for the relationship between time and distance, we do not need to specify how it would look. The computer can actually learn it. So we do not need to specify what is important in the relationship between time and distance. Okay? That's what feature selection means. We will see it in more detail as we go along, but for the time being, let's understand that if we want to learn relationship between two variables, an independent and a dependent variable, we do not need to specify what is important in their relation. Okay? Again, it requires fewer assumption. Basically, what you need is just input and output of a system, and more likely than not, you would be able to learn what the system is. Okay. The third thing, which is a drawback, which is it requires more data. So, for example, one apple falling from a tree might have been enough for Newton to understand what's going on, and a few experiments, and he could come up with his equations of motion. But the computer is not that smart. It would require more data. You would have to provide it with more and more data in order to learn more complex processes. So equation of, for example, distance covered under the action of gravity is not a very complex process. But if it's a more complex process, for example, finding a cat in an image or a dog in an image, it would require lots and lots of data. So that's one of the drawbacks of machine learning. And the last point, which is the risk of overfitting, often more difficult to explain. That's basically how good the function f that we have learned is. That's a property of that. So the f that you have learned might be good and general. So we have certain data here on which we trained our model. Now, our model might have one of the two properties. Either it performs poorly on the that we have f well. Okay, that's something that we call an unfit. Or it might perform very well on the that we have, but might not perform on other. That's called an overfit. So we would see what each of these terms is and how to avoid them and how to get around them. So this is actually an interesting slide. Hopefully people in the back can see it, but if not, I'll just try to highlight some things in this slide. So basically the first neural network was designed in 1957. So that's almost like maybe 60 years ago, more than 60 years ago. So what happened between this part and maybe up till 2006? Why didn't we see any use for neural networks? Why didn't we see them coming out like in a really dominant way, taking over most of the fields? That's one of the questions that we would answer in this small lecture series. But after 2006, actually it made a lot of progress and a lot of big things happened with machine learning. And that's when Jeff Hinton and coined deep learning and used it to distinguish objects in text and images and videos. So from 2010 onwards, 2006 onwards, machine learning was actually successful, somewhat successful, in understanding images and videos. And then we can see we could identify faces here, right? And we could see cats in videos. And this is probably not a direct application of convolutional neural networks, but these two at least, these are directly after Jeff Hinton's use of convolutional neural network. Okay, but some important steps happened in the 20 years, in the 60 years after 1957, which allowed us actually to use machine learning in our applications. So these are the 4 ingredients which are actually responsible for the, yes please. Yes. Yes, yes, because overfitting can only work with, during training you can do some sort of testing on a validation set. Okay, we will see how it's done. Yes.
I just want to.
Sure, sure.
Because when I look at
Yes.
which is that you have the data.
Okay.
So what is the difference? I mean,
It can depend on from field to field, but generally, yes, you can infer the dynamics and you can study the relationship between 2 variables, or you can see the relationship between an input which is a function of multiple variables and an output which is a function of single variable or multiple variables. But all these applications, so machine learning, any artificial intelligence algorithm which is primarily driven by data is an application or is a subset of machine learning. But generally you are trying to infer relations between data and its output. That's machine learning. Does it make sense?
yeah.
Okay. Any other questions? Okay, but that's good. Okay. So what has actually driven the recent you can say major strides in machine learning? So one is the field has matured in identity and methods and tool. We would see some of the methods and tools which has actually allowed us to use machine learning. But the second is actually the most important feature for the success of machine learning algorithms recently. That is, there is an abundance of data. And why do we have abundance of data? Because we have phones and we have internet, and we are just, each one of us is actually generating a ton of data each day now without even realizing it. So we have a ton of data now. So one of the application where machine learning is actually making a lot of money is the ads that you get on when you visit any website. If there are ads on it, these ads are suggested by machine learning. And how does it learn to do it? So basically the computer knows who is using it. Let's say you're using Facebook, Facebook knows who you are. And then it can see that, okay, if you are in Saudi Arabia and you are between 20 and 30, you are interested in sports, food, maybe, I don't know, books, reading. So then it would see another person and it would give it the same suggestion. And then it sees how many people are likely to accept that suggestion, and then it refines it. So that's basically, we are generating the data for the computer to learn what to suggest to us. So recent improvement, a lot of the reason for it is data. So we have data now. Okay? If you want a computer to learn to find a cat in an image, we are able to do it because we have like literally billions and billions of images of cats now, labeled ones as well. So we can give it to computer and tell it like, okay, in these images there is a cat, in these images there is no cat. And then computer can probably learn, okay, if you can see ears of a cat or nose of a cat in an image, say that there is a cat. But it wouldn't be able to do it with 1 image or 2 images or 10 images. It requires lots and lots of images. Okay. The third thing, there is an abundance of computation to run methods. So of course, if you say that you need millions and millions of images, well, you would need computation power actually to process them. And we have them now. We have supercomputers and we have GPUs which can actually process lots and lots of images in relatively faster amount of time. So we have more data and we can process it, so hence we can learn it. So that's basically like the formula for success. So we have resources, we have ingredients, we have tools, and we have desires. By the way, one thing that I usually add in the desire bit is that a lot of research and focus and money in machine learning comes from the big companies like Google, Microsoft, Facebook, and most of the tools that we use actually come from them as well. For example, PyTorch comes from Facebook, TensorFlow comes from Google. Any guesses as to why these big companies would be really interested in driving machine learning? Yes. Yes. So one of the reason, of course, it's beneficial for them, but there is a bigger reason than this, and the bigger reason is that if data-driven approaches are successful, then these companies are the winners because they have data. Okay. So, for example, if facial recognition applications are successful and they require billions of images, then Facebook and Google would have very good facial recognition applications because they have data. They have data with faces. But on the other hand, let's say if some of you in your research come up with a facial recognition application where you require maybe, let's say, hundreds and just 100 or 200 or 300 images, well, it would still be useful for Facebook and Google, but they might not be as happy about it because then everybody else has it too. So it's a kind of a supply and demand thing. So data-driven approaches are generally, a lot of the money in it is driven by big companies who have a lot of data. And this is just one interesting information that a lot of people are actually interested in it and they are spending their time to learn the field. So let's see what are the types of machine learning, or what are the types of learning. So the first type is supervised learning. So supervised learning is basically a type of machine learning where you have some data and you have the output label for that data. So the example that we saw where we are trying to find the relationship between distance covered in time t under the action of gravity, that's reinforcement learning. So you have xi, which is data, and you have the corresponding output yi, and you're trying to learn the function f which maps xi and to yi. Okay? That's supervised learning. Any questions there? Simple and straightforward. You have input of a system and output of a system. You don't know what the system is and you're trying to learn that system. That's supervised learning. Unsupervised learning, you just have some data and you want to learn something from it. Okay? You don't know the output of the system, you just have some data. So a simple example that I used in one of my previous lectures, let's say for certain disease, let's say for diabetes, we have, let's say, for diabetic patients, we have the data of their age and let's say their lifestyle. Okay? So lifestyle is a variable where good lifestyles, as you go up, your lifestyle is good. Okay? So maybe if you cluster the data, you will get something like that. In fact, it shouldn't be like this. It should be something like this. So this is just the data of two variables for diabetic patient, but we can actually see a relation in it. And the relation in it is that if your lifestyle is good, if you have a healthy lifestyle, you will, and you suffer from diabetes, you would suffer from it at a older age. If your lifestyle is worse, you will suffer from it earlier. So there was no output of the system. We didn't know anything. We just have some data for diabetic patients and we just plotted it in two variables which we have collected for diabetic patients, and we actually found that relation. This is unsupervised learning. So we didn't have any predefined output for the system. We just learn something interested from the data itself. And lastly, we have reinforcement learning. Reinforcement learning is basically the example of the robot that we saw in the very beginning. So you have a world, an environment, okay, in which you have an agent, which is the robot, and then it can perform certain actions, okay, move left, move right, or move up, and it can get certain reward. Okay, that's basically reinforcement learning. So you have an environment, you leave an agent in it, it is at a current state S, it can do certain actions, and it has to reach a destination to get a reward. Okay, any questions in this? Yes. Why would it want to? No, it's we specify it. Like for example, let's say I want to learn this algorithm for a robot to go there. So basically I would, for the 2D, I would make a 2D grid of the room. I would say that at each point in this 2D grid, you have no reward. But at this point, if you reach there, you get a reward of 1. And then I run simulations over and over again. Exactly, yes. So you learn and learn and learn and learn, and with time you update your policy. Yes, yeah, hopefully, in the previous group I could not show them an example of reinforcement learning, but hopefully for this group, if I have time, I have some good simulations of this reinforcement learning exactly like this. We want an agent to go to a certain position, and I'll show you that it actually learns the best policy, the best way to actually go there. Okay, but again, yes.
So,
yes.
solve this like a development?
Yes, it's generally it would be something like clustering or something where we'd want to, we have data, but we want to see if there is some relation between different pairs of this data. So it's something. No, there might not be any relation. That's unsupervised learning.
In supervised, you are sure there is a...
Of course, in supervised you are learning a relation. You are trying to learn that relation. Okay. And then supervised learning is divided into 2 further branches. One is regression and classification. Very simple, nothing confusing. The function f that we are trying to learn, if it's continuous, we call it regression. If it's discrete, we call it classification. Okay. So, for example, in the example of throwing of stone, we have a continuous variable, right? So a distance is a continuous variable. You can cover 20 meter, 21 meter, 20.5 meter. But let's say if you're trying to find a cat in an image, it's a discrete variable. You cannot have 0.5 cat in the image unless somebody has like killed a cat in a very bad way. You would either have a cat or you won't have a cat in an image. So it's a classification problem 1 or 0. Okay, that's just the. So now from here I'll just take a break because now we are going to do some real machine learning. The definition part is over. So we saw that we have artificial intelligence. Under artificial intelligence we have machine learning, and now I'm saying we would do an example of regression. So where does regression fall under this umbrella? It's machine learning. It's a type of supervised learning, and under the supervised learning it's a form of regression. Yes, please. Actually, that's something that I don't know exactly. But machine learning, I think there is some overlap of some statistical tool and some machine learning tool. But machine learning, I think, is probably more general than statistics. But I have seen that this is actually a tool which is used in statistics as well. But I don't know the exact answer because I'm not a statistician, so I cannot tell you for sure what's the difference. Okay, but linear regression, for me at least, is the simplest form of machine learning, and it's easier to show all the tools that are required in a machine learning application on a linear regression problem than any other problem. So we will start with this and we'll see where it goes. Okay, so some motivation for it. I would mostly focus on the last two because they're easy to interpret and they're efficient to solve. Okay. So let's see what do we do in linear regression. So like I said, in the application that I'm trying to solve today, I have a variable x and y is a function of x, and I'm trying to find the relation between x and y. Okay? So in this case, the relation that I'm trying to find, I'm saying that it's of the form mx plus b. So I'm saying there is a linear relation between the data x and the output y. But I don't know what that linear relation is, and I'm trying to find it. Okay? That's the process of a simple regression. That's a statement of a simple regression problem. Okay? So generally, if we want to define a line in space, how many points do we need? Just 2 points, right? So it seems actually, what if I just take 2 points and try to fit a line to it? Let's say I take this point and try to pass a line through it. That looks very different from how my data looks, right? Okay, so it doesn't seem to work if I take 2 points and just pass a line through it, right? I can take maybe another pair and see if that works. That doesn't work either. Okay, so that technique doesn't seem to work. You cannot take 2 points and pass a line through it. It would not represent your data very well in this case. Okay. Just some definition. So y is the response variable, something that we are trying to, that's the output of the system, x is the input of the system, and m and b are something that we would be trying to learn. That's basically the parameters of our model. So this is the summary of the simple linear regression. You have data in terms of inputs and outputs, x of i's and y of i's. And in the simplest example that we have seen, we would try to learn the variable m and b, which is the slope and the intercept. And we have already answered this question that the simple approach of just taking 2 points and connecting them would not work. So let's see what we can do. So here I'm showing that this simulation, like you can actually see that for some points it works, but for most points it doesn't work, taking 2 points and passing a line through it. So I'm proposing a solution strategy, and you guys tell me if you guys like it or not. Does it seem like a valid solution strategy or not? So my solution strategy is that I want to find, in some sense, an average line that represents the data. Okay? Something which would be, on average, equally good from each point. And now this is for you guys. So any ideas as how we should do it? Not the statistics guys who have already seen it, but any other guy, if you want to take a shot at it. How would you do it? How would you solve this problem? Where we are trying to, you have some data, there is a linear relation to it. You want to find that linear relation, but it would be like an average kind of relation. It would not pass through all the points. In some sense, it would, on average, minimize some quantity from all those points. So any guesses as to what should that quantity be, and how should we approach it? Okay, that's one approach. On average, you can try to hit as many points as possible. What else? Okay, curve fitting, that's actually the right answer. But how would we do the curve fitting? People who know curve fitting, I would want people who don't know the curve fitting to actually answer it. I want some organic guesses. Yes? Least square method, okay. That's okay, so we'll see. So basically what we do is, we would say that, okay, we are trying to fit that line to the data, and of course the line would not pass through all the data point. So what we can do is we can say that, let's say that my line is mxi plus b, okay, and the output for that point xi is y. So we try to find this quantity y minus mxi plus b. This is kind of the error between the result that you have proposed. So this is the real value which you have observed on your data, and this is the hypothesis, the proposed value, which your system, your learning method has proposed for that data point, okay? And what you're trying to do is you want to minimize the discrepancy between these two. Does it make sense? Does it seem like a reasonable assumption? You say that basically on figure, if you want to see it on the figure, basically what you're trying to do is you're doing this. You're saying that you want to minimize for each of these points, you want to minimize this quantity. I'll call it EIs for different I. Where EI is yi minus mxi. I'm sorry? We want, yes, we want it as low as we can, yes. One thing I've actually done wrong on the slide intentionally. So the definition that I have, y minus mx plus b, it's actually not true, because if you want it as low as possible, it would force mx plus b to infinity or negative infinity, right? Because it would give a negative value, and negative value are lower than positive value. So we want them smaller in magnitude, okay? So the simplest way to make a quantity smaller in magnitude is to do this. So we would try to minimize the square of the discrepancy between your hypothesis and the result that you have observed. Does it make sense? Okay. And then of course we don't want to do it for one data point, we want to do it for all data points. So we would sum it from I equal to 1 till n, where n is the number of data points. Okay. This seems like a good start. We have something reasonable that we can actually work with. Any questions up till now? Let's just wait for a bit. It would come in a bit. You probably won't see any overfitting in this because this is the simplest possible method. But let's just wait till the end of the lecture and we would see where the overfitting comes in. Okay. So this is the model that we are trying to propose. So we are saying that for each data point xi, you find the hypothesis of that, you have the output yi, and then you have a loss function or a cost function whereby you minimize the discrepancy between the two. A question, so this is basically the cost function j. What are the independent variable of my cost function? What does my cost function depends on now? What are the variables that I would change and my cost function would change? No, these are explicitly mentioned in this. Just tell me the name of those variables. I'm sorry? Yes, the m and the b. Okay? Because xi's and yi's are not variables. This is the data that you have collected. Okay? And as you vary m and b, your loss would basically either increase or decrease. And as you're changing m and b, this is what is happening. So for some m and some b, this is the line. For some m and some b, this is the line. And you can see that probably the best among the three that I have drawn, the red one is probably the m and b for which the loss function would be minimum. Okay? So that's actually the flow chart of the linear regression process, and we would try to find the M and B which minimize this loss, and then hopefully we would have something reasonable. So let's look at a simple example just to see how the cost function looks. How as we change the independent variable of the hypothesis, how does my... So I make the problem slightly simple. I say my hypothesis function is a function of one variable. It's not dependent on B anymore. It's just h is equal to mx. Okay? And let's see what are the three data points that I have. So I have three data points, xi's and yi's, and this is for x equal to 1, I have y equal to 1. For x equal to 2, I have y equal to 2. And for x equal to 3, I have y equal to 3. Okay? So question, what would be the x-axis of the cost function? What is the independent variable of the cost function in this case? Sorry? X? But x are fixed, we have fixed them here. It's m, right? As we vary m, our cost function would change. So the independent axis of the cost function is m, and this maybe we can call it error, the y-axis. So let's try to write the cost function for this case. So I have for I equal to 1 to 3, yi minus mxi whole square. Okay? This is the hypothesis, and this is the observed value. Okay? Any questions? J as a function of m. So I will write it, and this would becomes Jm is equal to summation I equal to 1 to 3 I minus mi whole square. I can do it because I have chosen I such that I is varying from 1 to 3, and so the label and the x component of the data point is equal to the data point. Okay? I'm sorry? Yeah, it's the same. You wouldn't be able to write it like this in every case, but this is just for some demonstration purpose, I have done it like this. Okay? So let's set m equal to 0 and try to find what's the value of j. So I'm trying to find j at m equal to 0. Okay? So if I put m equal to 0, I will get 1 square plus 2 square plus 3 square. Does it make sense to everyone? Please, if at any point you have question, just ask it. Okay? Everybody agrees with the loss function at j equal to 0 being this? Okay, perfect. So that would be something like, its value is 9, 10, 14. Okay, so it would be somewhere here. Okay, this is 1 is 5, 5, 10, and 15. Okay. Now I'm trying to find the cost function at m equal to 1. Okay, and that would be 0 square plus 0 square plus 0 square is equal to 0. Does it make sense to everyone? If m is equal to 1, my loss function becomes I minus I whole square. So it's 1 minus 1 whole square, 2 minus 2 whole square, 3 minus 3 whole squares, 0. So at 1 I'm getting a 0. And now I do it at 2. So it would be 1 minus 2 whole square. So this is 1 square, minus 1 square, but minus 1 square is 1 square. Okay. And then at 2, so this is 4 minus 2 whole square, 2 square, plus 6 minus 3 whole square is 3 square. So this again is 14, and I draw it here.
And if I repeat the process, I see that I get something like this. So this is a convex function. And for a minimization problem, convex function is something that we love. Okay? Why do we like convex functions for a minimization problem? Can you raise your hand so that I can see? Yes. Exactly. Because there is one minimum, and that's a global minimum. So that's perfect situation for us. If you find it, you have found the best solution for your system. So it seems like a very good cost function, the cost function that we have found here, okay, that we have defined here. A question though, so the global minima that I have found in this case, it has, the cost function for this is equal to 0. Is it always guaranteed that for linear least square, the cost function would always be 0? No, right? Even in this case, like if I assume that there was some noise in my process, so if I assume that there is slight noise in my process and your points are moved slightly, well, you will not get zero cost function at 0, at m equal to 0. You would have some discrepancy. As you can see that you have some discrepancy between the line and the data points. Okay. So basically, up till now, we have looked at the problem of linear regression. We're trying to find the relation between an input x and the output y for that x. And we start with writing a hypothesis function for the process. Hypothesis function is what we believe the process looks like. Okay? And then we try to fit the parameters of the hypothesis function to the data. We write a cost function for it. The cost function is the square of the discrepancy between the hypothesis function at each data point and the label of that data point. We add them up and we see that it's a convex function, which is a good function, and we can find its minima. So we will take a short break here, 5 minutes, just freshen up a bit, and at 10 we would come back and we would see how do we find that minima and how do we actually fit our hypothesis function to the data. Okay, short break and see you guys back in 5 minutes. Okay guys, guys, can I have your attention? Let's settle down. Guys, thank you. So I'll just do a quick recap. We have settled the problem of linear regression. What do we want to do? We want to fit a hypothesis function for the independent variables to the observation of the dependent variable that we have. And we have seen that it's a good cost function. Now we'll just try to find the solution, the global minima for that cost function. So let's see how we can do it. So I'll just carry on this problem to the next slide and we'll see what to do. So I have this data that I have observed for a very reasonable and simple process, and we just want to see how to find the best solution that would fit our data to the outputs that we have observed for their data. And our hypothesis is a function of one variable. It takes in an input xi and gives you an output m of xi. Okay? And the cost function we saw on the previous slide was I equal to 1 to 3, I minus m of I for this particular process. Or I would write it in some detail so that there is no confusion. So that was 1 minus m1 whole square plus 2 minus m times 2 whole square plus 3 minus m times 3 whole square. So these are xi's. sorry, yi's, and these are xi's. Okay, so from the table I just substitute the values in this my equation. Clear to everyone? Now I want to minimize this function with respect to m. Any guesses how to do it? How would we minimize this function with respect to m? Sorry? Okay, so we do the standard thing in calculus. We take its derivative and set it equal to 0. Okay, so you take the derivative of j with respect to m. That would be 2 times 1 minus m plus 2 times 2 minus 2m times 2 plus 2 times 3 minus 3m times 3 is equal to 0. Everybody understands this? This simple derivative, simple chain rule. So you apply the power rule to the entire thing and then you take the derivative of what's inside. Okay? If anybody has confusion here, please let me know and we will settle it. Okay. So we just collect terms. So this is 2 minus 2m plus 4 minus 4m. Sorry, 2 times 2, 8 minus 8m plus 6 times 3, 18 minus 18m is equal to 0. I could have taken 2 out, but it's fine. You can write it like this. So this is 2 plus 8 plus 18 is 28 minus 2 times 8 plus 18 minus 28m is equal to 0, and m is equal to 28 divided by 28 is equal to 1. Okay. So we did indeed find the global minima. Okay. So that's actually quite convenient. We didn't learn any new mathematical tools. We're using the simplest relation from calculus, where we know that if you want to find the optimum points or the critical points of a function, you set its derivative to 0. It can be either a minima or a maxima or a critical point or a point of inflection. The good thing is I don't need to check it here whether it's a minima or a maxima. I know that it's a minima because it's a convex function. Okay, so no need for checking the sign of the second derivative. Okay, so everyone can now, I hope, find the optimum solution or the best fit to a data for a single variable. Now let's extend it, because of course very seldom we would require to fit data where the relation is a single variable. We would probably require something which is more complex. So let's see if we have 2 variables, what would happen. And you guys have to help me. We'll just generate an example on the go and we will see how it looks. Okay, so let's take an example where we have, so for x equal to 0 we have y equal to 1, for x equal to 1 we have y equal to 2, and for x equal to 2 we have y equal to 3, and for x equal to 3 we have y equal to 4. Okay, so if I plot it, this looks like this. The slope is 1 and bias is 1. Okay, so now we would have to use a slightly more complex hypothesis function, because hypothesis function of one variable would not work here. So I propose to use I would increase the complexity of my hypothesis by one variable, and I would say now my hypothesis function, Now my hypothesis function looks like this. It's a function of two variables m and b, and it is equal to mx plus b.
Okay?
So my loss function would also become a function of two variables m and b, and it would be summation from 1, 2, 3, 4, from I equal to 1 to 4, y of I minus mxi plus b whole square.
Everybody agrees up till here what I've done? Very simple. I've just written a loss function for my hypothesis function.
Okay.
How do I find the best values of m and b for this loss function? And you raise their hand and tell us how to do it. So in the previous case, I had a cost function which was a function of one variable. I took its derivative and I set it equal to 0. Now we have a function of two variables. What should I do to find the best solution for it, or the global minima for it? Not you, someone else. Okay, so we find the gradient and we set it equal to 0. Okay, so you find the partial derivative with respect to each variable and you set it equal to 0. Okay, so let's do that.
So let's first find partial derivative of j with respect to m. I'm going to do something. I'm going to multiply it by a factor 2.
You would see why it's good. It just cancels out the 2 in the power. And just to show that it doesn't change anything else, just dividing it by 1 by 2 just changes it maybe to something like this, which is still convex and does not change anything. Okay, you would see when we go slightly more ahead that we actually normalize the cost function with the number of data points as well, which makes calculation slightly more convenient, but again it would not change anything. It would just make your loss function like this. Okay, but for the time being, let's not look at these. Let's just look at the simple concept and try to solve it. So let's take the partial derivative of this with respect to j. So that would be, I can of course take the partial derivative inside the summation side, inside the summation sign. So that's 1 by 2 I equal to 1 to 4 2 times yi minus mxi plus b, okay, and minus xi. Does it make sense? Is it correct? Yeah, seems fine. Okay.
So just and I had of course have to set it equal to 0.
Okay.
So I can remove this minus sign and I can remove these.
Right. I'm just multiplied everything with -1. Does it make sense? Because it's equal to 0, so I multiply both sides by -1, so the minus sign is gone.
And that would be now I equal to 1 to 4 xi yi minus m xi square. No, I think I'm doing the mistake. So let's see. Let me try to write it explicitly and try to solve it. So I have 1 by 2 1 minus m times 0 plus b whole square plus 2 minus m times 1 plus b whole square plus 3 minus m times 2 plus b whole square and plus 4 minus m times 3 plus b whole square. Okay, I have to take the derivative of j with respect to m and set it equal to 0, and I have to take the derivative of j with respect to b and set it equal to 0. Now when we set these two derivatives, partial derivatives equal to 0, we would get a system of equations. We would have to solve a system of two equations and two variables, and we would have to find the optimum value of j and b. So we already have to use a system of equation to solve this system. A better thing to do is actually to vectorize the system and write it in matrix form so that you can actually use it more conveniently. So we would see how to write this in matrix form, and maybe it would help us solve it in a more efficient and more optimal way. Okay. Okay. So my data was xi and yi. For 0 I had 1, for 1 I had 2, 2 I had 3, for 3 I had 4, and for 4 maybe I had 5. My hypothesis function in B takes xi and gives you mxi plus b. Okay. So what are my unknowns? My unknowns are m and b. Okay. And what is my real value for my function, or the y, the observed data? That's 1, 2, 3, 4. Let me add another point as well. 5 and 6. Okay. Now I want to write this y as a hypothesis function which takes in an x and give you mxi plus b. Okay. So for y equal to 1, what was x? It was 0, right? So I can write it 0m plus b, right? So I'm just doing this. I'm saying that take this x and put it in this hypothesis function. So h of 0 is equal to m times 0 plus b. Okay, so this is m times 0 plus b, and the corresponding value of y for this is 1. Does everybody understand this vectorization? So basically I would just write it here. I have a set of equations. So basically for y equal to 1, I have 1 is equal to 0 times m plus b plus some error that I am trying to minimize. Okay. For 2, y equal to, for the second point, when y equal to 2, I have 1 times m plus b plus some error. Okay. For 3, I have 2 times m plus b plus some error, and so on. For 6, I have 5 times m plus b plus some error. Okay. So I have written for each of these data points, I have written a relationship. So my relationship is the observed value is equal to the hypothesis function plus some error. So this is observed value is equal to hypothesis function plus error. Okay, does it make sense? If something is confusing, please raise your hand, so that, because this is like the main contribution of today's lecture. If you can vectorize the system like this, it's very easy to solve it after that. Okay, so I just collect these equations in the big matrix form, in the big vector form. So this is 1 and 1 and 1, 2 and 1, 3 and 1, 4 and 1, 5 and 1. Okay, plus an error vector E1, E2 up till E6. Everyone agrees with this matrix form for my system of equations? Okay. Now, in order to find the best values of M and B, what do we have to do? In this case, what would we minimize? Anyone who is not from statistics would like to? So what is the error between our hypothesis and the real result? Where is that error in my equation? It's that vector, right? That vector kind of represents the error between the actual observed value and the value that my system is proposing. So ideally, I would want my proposed value to be equal to this. So I have to make this as close to 0 as possible, right? So I'm trying to basically minimize these errors. Everyone agrees with this? Yeah. So we want to minimize these errors, and I can write the objective of my KAUST function as this. So my KAUST function is a function of M and B, and that is from I equal to 1 to 6 EI squared. Okay. So I'm trying to find the square of the error for each data point. I'm summing them up and I'm saying let's make it as small as possible. Fairly reasonable, right? So let's see how we can do it. So I have this vector E. I would represent it with a bar on top. So I can write the same thing as E bar transpose time E. Everyone agrees? This is basically this. I'm taking the matrix product of E1, E2 up till E6 with E1, E2 up till E6. And you just do the matrix multiplication and you would see it would be a 1 by 1 matrix, which is a constant with a value E1 square, E2 square, E1 square plus E2 square plus E3 square up till E6 square. Okay? So I'm just going to do some more representation. I will call this Y. Okay? I'll call this matrix A, and I'll call this matrix Z. Okay? In this objective function, I have to find Z, to find M and B. Okay? So now my function, my Y is equal to AZ plus some error, and I'm trying to minimize E transpose E. Okay, and I can find what is the value of E from this equation. This gives me E is equal to Y minus AZ. Okay? I'm just trying to, I will put this value here, and this will become minimize Y minus AZ transpose times Y minus AZ.
Everyone agrees with it? Just simple substitution, find the value of error vector, put it in the equation. Okay?
And now, of course, our unknown are the vector Z. We're finding Z. So I take its matrix derivative with respect to Z. So d by dz of Y minus AZ transpose. I'm trying to write them bold, but you understand that these are all vectors and matrices. Y minus AZ, and that is equal to A transpose 2 times A transpose Y minus AZ is equal to 0. This is an identity from matrix calculus. Okay?
Is it clear up till now? Any questions?
Okay. So we just do some rearrangement of terms. We get A transpose A. I can remove the 2 because we have 0 on the other side. A transpose A Z is equal to A transpose Y, and then Z would be A transpose A inverse A transpose Y.
That seems much more convenient than, I don't know, adding all these terms up.
I just gave it a try and I got lost.
I said, okay, let's leave it, let's not do it, let's go to the vector form. So you saw that I was trying to find the derivative of each term, but again, it's not that straightforward, so
It's better to just stick to the vector form.
much more easy, much more convenient. All you have to do is just construct this matrix A for your hypothesis function, and that's it.
So you can see that Z
Is just a function of A. You just have to construct the hypothesis function, the A matrix for the hypothesis function, and that's it. Y you already know. You can just take the matrix inverse and you're good to go. Okay?
So we've already covered the solution for the linear least squares. What I'm going to do is,
Yes. Yes. Yes, but we already showed that the objective function is convex. Exactly, yes. But you can, if you want to check, you can. In this case, you just check find the Hessian of the function and show that all the eigenvalues are greater than 0. So you can, for a single variable, we find the first derivative, we set it equal to 0, that would give you a minima, maxima, or a point of inflection. Then you look at the second derivative. If the second derivative is greater than 0, it's a minima, right? In this case, in more than one variables, you would find the Hessian matrix and show that Hessian matrix is positive definite. And positive definite means that all its eigenvalues are greater than 0. Okay?
so let's take, I'm sorry. So far we have seen actually
Very simple systems like something like linear functions, linear function with a bias, linear function without a bias. But of course our function can be as complex as they come. What can we do? So basically I select that if, let's say, you have some data xi's and y's, and they can be quite complex. The relation between them can be quite complex. So I can write a hypothesis function, which is a function of a vector theta, and it can be actually slightly more complicated. It can be theta 0 plus theta 1 times x plus theta 2 times x square plus theta t time, and so on. Anybody agrees with it? Sorry. This is x. Okay. Everybody agrees with that? You can, hypothesis function, you can make it as complex as you want. It doesn't have to be just linear and independent variable. Is it still linear regression though? Is it linear in the unknowns that we are trying to find? Yes, it's linear in theta. Okay? So it would still be convex. The objective, the loss function that you try to find out, it would still be convex, and you can actually still try to solve it. Okay? And I claim you can actually find any function with this. So for that to happen, polynomial functions would have to be a basis, right? And do polynomial functions form a basis? Yes, they do. And we already know it in some series that we already know, where we actually use polynomial basis to approximate a function, at least locally. Can anybody tell me what that is? Taylor series, okay? So we've covered all the bases. Let's see what we would do in order to solve that system. Let's say we have any complicated function, we have certain number of bases. Let's say I would say that this is up till theta n x power n. Okay? So let's write the system of equation, and I'm saying that I have m data points. From 1 to m are my data points. Okay? So I can probably write it like this: y1, y2 up till ym. This is some matrix A that I have to construct. What do I have here? I have theta 0, theta 1 up till theta n. How many columns should my matrix A have? Sorry? It should be n plus 1, because we have theta 0 as well. Okay? So n plus 1 columns. And how many rows? Sorry? M rows. 1 for each data point. Okay? And we can see that in our hypothesis function, the weight for theta 0 is just 1. Okay? So we can say that this is just ones. Okay? The weight for theta 1 is x, right? It takes in the data point and gives, so this is xi. So this would be x1, x2 up till xm. Everyone agrees with this? What is the weight for theta 2? X square, right? So this would be x1 whole square, x2 whole square up till xm whole square. Okay? So on. What would be the weight for xn? Sorry, theta n. It's x power n. So this would be x1 power n, x2 power n up till xm power n. So now once we have this matrix A, we can find theta as A
transpose. That's technology. Okay, I'll just quickly write it again. So y1 till ym equal to 1, 1, 1, 1, 1, x1, x2, xm, and up till x1 power n, x2 power n, xm power n, theta 0, theta 1, till theta n. That's it. That's A, that's Z, that's Y. In fact, let me call it theta now because it's a vector of theta, and theta is equal to A transpose A inverse transpose B, A transpose Y, sorry. Okay. This, by the way, is also called linear least squares, and you can find a lot of literature. I think probably that's what statistics people call it, linear least squares. Okay. So now basically we have tools to fit any function that we like and get a solution for the given data that we have. Okay. So I actually have written a small function for that. So let's see if we can have some here. Meanwhile, if you guys have any question, please feel free to ask. Okay, so let's see what I'm doing here. That's probably, how many of you are at least somewhat familiar with Matlab? Okay, so I'll actually explain what each line does. The good thing with Matlab is that it is like very close to like English, so you can actually understand it. You don't need to be very good at programming or anything. This, by the way, is my email. If you have any questions or suggestions, please feel free to contact me. So we want to generate some data, and then we want to learn a function to fit the input to the output that we see in that data. Okay. So the first thing I do is I generate some values of x's. So I say my x is from -1 to 1, uniformly with uniform step of 0.01. Okay. So this would be -1, -0.99, and so on up till I think we would have 201 points. Okay, something like that. Then I say, okay, let's write a function for this x, and that's heaviside of x, step function. Somebody in the last class actually asked for it, so I put it. We would change it and we would see what happens. Then I say, okay, let's make it slightly complicated and let's add some noise to it as well, to our function. So I say that the noise amplitude is 0.1, and just add some random noise in this function with the magnitude of, this is normal distributed random noise, so Gaussian noise with an amplitude of 0.1. So some randomly added noise to my function y. Okay. Now I say, okay, how many bases do you need for your hypothesis function? what is the maximum power of x that you want in your polynomial approximation of your function. Okay, and I say I go up till x power 10. Okay, so I have to generate the matrix A. So I say that A is just from I equal to 1 to n plus 1. A is A comma x dot power I minus 1. So let me just tell you what this for loop is doing. When you come in this for loop, A is empty, I equal to 1. So in the first column of A, it puts x power 0. So it's all ones. Okay? For I equal to 1, in the first column you have all ones. In the second column you would put x power 1, which is x1, x2, x3, x4 up till x201. Okay? In the second column, in the third column you would have x1 square, x2 square, x3 square, and so on. In the fourth column you would have x1 cube, x2 cube, x3 cube, and so on. So basically this is generating the matrix A for us, exactly like we have designed. And so on. And then of course Z is just A transpose A inverse A transpose Y. Okay? So now I have the weights that I want to assign to each of my bases of A, each of my polynomial bases. So I just, I can do this probably, this is better. So I just, to find the value of the function Y for my hypothesis, I just multiply Z with A. Okay? And I plot this and the original one, this, and give it labels. I think rest is not, for those who don't understand Matlab, just forget about this. This is just some plotting thing. But I'm just plotting the real value of Y, which I have generated here, the input and output, and the value that I have found. I call it Y found. Okay, and let's see how it looks. So Heaviside function is a step function. It's 0 for x less than 0 and 1 for x greater than or equal to 0. So let's see. It looks good, doesn't look very bad. So this is my data. Of course it's not 0 and 1 because I have added some noise to it. Okay. So this is how my data looks, the red points. Okay. And the blue point is actually my function, the one that I have learned from my data. Looks fine. Doesn't look terrible. Okay. Any questions? Yes. It's Heaviside function, but you have added some noise to it, so it doesn't look like Heaviside anymore. But let's remove the noise and let's see what happens. So now you can see that the function that you have to find is just zeros and ones, but what you find is something like this. It's fine, not amazing. Anybody want to take a crack at it? Why? Why is it not approximating it very well, particularly near the discontinuity? Because generally for like well-behaved bases, like let's say cosine bases and polynomial bases, you would require a lot more bases to actually find this thing, the jump, to actually model this jump. So if you keep on adding more and more terms, hopefully at some point you would find it. But there is some added constraints to it. As you add more and more to it, your matrix might become more and more ill-conditioned. So it's not that simple. But for test, let's see. Let me make it from 10 to 100 and see what happens. Okay, that's better. At least better than the previous one.
So it seems like we have something on our hands. We can actually find functions. If you, all you need is data, and you can actually fit, learn a function to fit the input and output of that data. There must be some questions right now, because now you see it on the board. It's not just me writing some equations. Okay, I'll ask you a question. Just tell me a good function, and let's see if we can fit something to that. So we have some warning here. It's probably because our matrix is not very well conditioned, but that's fine. For the time being, we are not looking into it. We try to, okay, tell me some good function of x. I'm sorry? Somebody raise your hand and tell me a function of x. Yes? Gaussian? Exponent of minus x squared? Okay. Yeah. Okay, that should be fine. I'm going to make it back to 10. Okay, it's fine. Somewhat Gaussian. Of course, we have not normalized it, so it's the probability distribution. It doesn't look like a probability distribution, and we have added some noise to it as well. So works on exponent negative x squared. Anything else? Anything else that you guys want to see? Yes, please. Yep. So basically, this is an interesting question. Why do we get this oscillation? So basically, you will have this oscillation because you're trying to model a discontinuous function with continuous basis. Okay, there is a name for it in the theory of Fourier series. I'm forgetting it, but you can minimize it, but it will always be there. Okay. Yeah. Yeah. I think it probably we might be able to remove it with some regularization. I haven't actually done it. I've never actually tried to fit a Heaviside with regression, at least on polynomial basis. We have done it in Fourier series, and we do it in with Fourier basis with cosines. But yeah, maybe in the next lecture when we do regularization, we can see why it happens. But generally, the problem is because you're trying to model a discontinuity with the polynomial basis with continuous functions. So basically what is happening is, if I roughly explain, hopefully that would work. So at this point, your derivative is very, very high. It's like very high. So in order to approximate the function at this point, your regression actually adds a lot of polynomials, all the polynomials which have a positive gradient at this point, in order to match this sudden rush of gradient. And then because of those additions, you get these oscillations. It's easy to see in the cosine, but that's an interesting observation. And the completely correct answer would be that I don't know. Okay, but we will see. We can see in the coming example. Okay, anything else? Any other functions? Somebody please raise your hand and tell us a function, and we can see whether we can model it. A complex function, like a difficult one. Come on. I'm sorry? Sin x divided by x. Okay. I'll do it sine of x dot divided by so we don't want it to be divided by 0, so I've just modified the function slightly. I've added it the absolute value of x and plus some epsilon. Okay, but that would be
I'm assuming that it would be something, let's see, no need to assume, let's have a look. Okay, so let's make it sine of 8 times this so that we can at least see one cycle of it. Because from -1 to 1, you don't see a complete oscillation of sine. Multiply it with 2 pi and then you see. So I'm going to multiply it with a positive number so that, okay, yes, so it makes sense. At 0 you would just go somewhere else, and other than that it's reasonable. Again we see these oscillations, and my guess still remains the same. It's probably because of the discontinuity. But the thing is, the good thing is that it actually works. Okay, so if you have, in your research problem, if you're trying to model a function, you can now do it with the polynomial basis, and you can actually learn the weight of each of these bases. Those of you who are actually in electrical engineering, you have already done it, but you call it Fourier series, and you use Fourier bases. Okay, but you have already done that regression without actually probably knowing it that you can do it. Yes. Of course you can. What do you want it to be? Minus, I'm just going to use -5 and 5 because I cannot hear you. It doesn't even have to be symmetric, it can be anywhere. The thing is that now the function becomes difficult to model, because now it's from very big, it has to go to very small. So it has to, for some point, it has to say that, okay, I'm sorry, I cannot model these points. So it just say for these big ones, it says that, okay, these one probably would not be modeled very well. If I had to guess, if I had actually put a guess on it, I would have said that it probably would take in these points and then probably forget about these points, because you can see that the absolute error is very high for this one. You are taking square of error. Okay, but maybe if it's these points, then maybe it's slightly higher here as well, something like that. I cannot tell you exactly, but that's how it looks. Okay. Let's look at a problem of an overfit. So underfit is actually easy to see. If I want to show you an underfit, I would do this. I would just say that, let's say 1. This is the function. So this is an underfit. You have a complex function and you're trying to model it with a linear function. Okay, and it just tell you, okay, put everything equal to 0. Okay, and I can tell you that this is the best solution without even looking at it. Why? Because you can see that the function is odd function, so the bias would be 0. Because for each function, let's say this is +1, this is -1, and you have to find a b which minimizes the difference between all of them, so it has to find 0 is the best option in terms of square. And in linear, you can make the same argument about the linear one. So it's just 0. 0 bias, 0 linear component, nothing. That's an underfit. Now let's try to look at an overfit. Can I show an overfit in this example? I think I can. Okay, so what can we do? So we have a total of 3 data points, and we are taking, let's say, a total of 5 bases, and we have some noise. In fact, let's not do it. Let's keep it simpler so that we can understand it actually really well. 3, 2, 3, 7 data points, and you actually need 2, 5, and you have some random noise. Hopefully that would show it to us quite well. No, we just need slightly higher noise. A little bit more. No, that's fine. It's fine. I shouldn't do it. I should do it from -1 to 1. One reason when I was keeping the signal between -1 and 1 because then I can actually see the number that I put for amplitude actually matches the maximum amplitude of my signal. So there was a reason for it. I shouldn't have changed it. Sense? Okay. So this is an overfit. Okay. Can someone explain to me why this is an overfit? What is the function that I'm trying to learn? Y is equal to x. What? It's a linear function. And what have I? Yeah, it's a piecewise linear function. And what have I learned? Well, this is not, at least this is not linear. And this is not actually piecewise linear. It seems like piecewise linear because I'm plotting it for certain points. So let's see exactly how this function looks. So I'm just going to do some more coding. Does everyone understand what I'm doing? Hopefully that would work. And I will explain what I'm doing. So the function was not piecewise linear. This is how the function looks. It looked like piecewise linear because I was plotting it for a certain number of points. So let me just explain what. This is the data points, the training set that I have. Okay, and previously I was just a function and then showing you on the result on the training set because the training set was quite densely sampled. But now I'm generating a new test set. New data. Testing between each, between -1 and 1. Training, you're taking a point with a step size of 0.5. And for testing, I'm saying take it with 0.05. Okay. So that's why you see the actually true behavior of this. In fact, let's check it maybe with something else as well. Any other function that somebody wants to do? But let's talk about overfitting in a bit detail. So you can see that what we actually have learned is not what we wanted to learn. We wanted to learn a linear function. But we learned something which is like, I don't know, some high order polynomial. And this happens when the model, the hypothesis is more complex than the function that you're trying to learn. Okay? And there is a way to actually fix it. There is a way you would learn how to fix it. Not just for linear regression, but in general. But you guys should know by the end of today, things that I want you guys to like keep in mind is regression. The basic concept of regression is that you have data and you want to learn a function that fits it. That's precisely what you want to do in machine learning. Of course, all the models would not be as simple as regression, where we know the basis and we just want to find the optimum weight of each basis. It can be much more complex, the learning process. But the fundamental idea is same. You have data which has the independent variables and the dependent variables, and you're trying to learn the relationship between the two. And you learn it by learning a hypothesis function. In linear regression, the hypothesis function is the linear combination of polynomial bases. Okay? It can be much more complex than that, and we would see. The other thing that this should take from you is that the hypothesis function is not a completely independent quantity. If you don't choose it well, you would get an underfit
or an overfit, and you have to find the right amount of complexity for your model. Okay, that's it. If you guys have any question, please ask. We have 4 minutes. I'll leave it for questions. If you don't ask question, we'll just sit silently. I can assure you that would be more awkward than asking questions. So ask questions. Matlab code, okay. Yes. X has? Z is what you want to find, yes. No, no, no. A has just the polynomial basis. Yes. So and the output that is in Y. Is Y, yes. So I'm sorry? Yes. Y is the output of function X, yes. It's inside A, yes. A is the hypothesis function, A is the basis of the hypothesis function, and Z is the weights of the hypothesis function. So when you multiply A with Z, you get the hypothesis function. Does it make sense? A has the polynomial basis of the hypothesis function. X power 0, X power 1, up till X power n. If you remember, our hypothesis function had a theta here as well. Theta 0, theta 1, theta 2. This theta 0, theta 1, theta 2 are in Z, in Z. And we don't know what they are, and we are trying to find them. Okay? So basically, you have to find a Z which would make AZ as close to Y as possible. But you don't know the Z. You know the Y though. So you find the Y minus AZ whole square and you minimize it, and it tells you that Z should be this. And then once you find Z, you just do this equal to AF times Z. So this is the basis of this is actually your hypothesis now. You're multiplying the polynomial basis with the weights of the polynomial basis, and that gives you your hypothesis function. And then you just plot it. Does it make sense? Okay. Any other questions? There must be some. It's simple, but it's not that simple. There must be some. Okay. Let's sit silently. No, generally for machine learning we use Python, but this is just for illustration purposes. I think probably Matlab would be more easier to understand for people, so I just made these simulations in Matlab. PyTorch. And generally the accepted convention in academia is that PyTorch is easier to use, but if you want to make some packages like a professional one, then you use TensorFlows. Yeah, yeah. Okay, that's it. Thank you very much. See you guys tomorrow. Hopefully it was helpful.